Right, so here's an actual photograph from a paper done by a Canadian, Watson. Here's an outer layer of steel casing. Here's an inner layer of steel casing. And this is the cement where there has been channeling. Okay, so you can hardly expect that to be a seal against flow of fluids from down below. That's what it looks like when it fails. Okay. So how often does this happen? That's really the key question. Remember, the myth is that this is rare. Well, let's talk about rare for a minute. I need a break here. How rare should be the structural failure of a commercial jet aircraft? How rare should be the structural failure of the bridge that you drove across to get here tonight? Oh, you can't have never. Come on, this is the real world. No engineer can ever design something that will never fail. We always design to an acceptable level of probability of failure. And in most engineering structures, societal structures, structures in which society is expected to live or be transported, a bridge, an aircraft, or a building, there are legal requirements on what is called rare. You get on an airplane at the airport. Where's your nearest airport here? St. John's. You get on a commercial jet aircraft, by law, Canadian law and US law, the operator of that aircraft and the builder of that aircraft have to have shown by test and by simulation that the probability of that airplane losing its structural integrity is 1 in 10 million. Does that make you feel safe? Bridges, same thing. You're driving across a bridge, the probability that you're not going to get to the other side of that bridge, 1 in 10 million. What's rare? Would you accept 1 in a million? I would. Space shuttle, the astronauts, they had to accept 1 in 60. How do I know that? How many shuttle missions were there? Roughly 120. How many of them had structural failure? Would you get on an aircraft where the probability of it crashing from structural failure is 1 in 60? Astronauts are brave people. Okay, so let's look at rare in the context of oil and gas, in the context of cement or casing failures. This is industry data from Schlumberger. The authors of this paper went out and tested thousands of gas wells and oil wells for leakage, migration, vent pressure. And they found the following data. This is the age of the well, because they tested new wells as well as old wells. The vertical axis, I'll read it to you, it's the percentage of wells affected by sustained casing pressure. In other words, there's gas coming up outside the well. There are two things you should notice in this data. Let's look at the young wells, new ones. What's the rate of failure? Read it. Say it out loud. Say it loud enough for Fredericton to hear it. 5%. 1 in 20. Is that rare? Okay. What's the other thing you notice about this data? Those of you with arthritis. Every engineering artifact, including our own structures, I am a structure, you are structures, as we age, things go bad at a higher rate. So by the time you get to aging wells, where are we now? 50 to 60%. It's industry data. I promised you I wasn't going to show you any data that I pulled out of the sky. It's industry data. Okay, so I showed this data to the Environmental Protection Agency in Washington earlier this year at a workshop, and the people sitting behind me from Halliburton. And I got to describe this. These two guys came into the meeting. There were 30 representatives of the oil and gas industry. There were a couple of professors. There was one representative of the NRDC, and there were about 20 people from the Environmental Protection Agency. And the purpose of the workshop was for the industry to inform the Environmental Protection Agency about their practices. Okay. So I get up and I show this data, and I say, you know, we have a problem here. And the guys from Halliburton, cowboy boots, string ties, the guy threw down his copy of the USA Today where he was doing the crossword puzzle. I'm serious. I turned around when he stood up. He had the crossword puzzle open for USA Today. That's what he was doing while the rest of us were practicing good science. And he said, that's for offshore wells. This is this spring. Remember what happened in the summer of 2010? And I turned around and I said, you're from Halliburton, you should know. He didn't like that. So I said, okay, fine. I went home and I did some more literature review, like I'm sure your natural resources department is doing. And I went to the Canadian literature and I found this. This is that same Watson and Bachu, Society of Petroleum Engineers, publication 106-817, 2009. So this isn't ancient data. This is data taken from 352,000 Canadian oil and gas wells. So it's a big database. And I'll explain it to you. There's two graphs here. This one, these black lines, is the percentage of wells with sustained casing vent flow or gas migration. And as you can see, the failure rate varies with the age of the well, as you'd expect. Young wells fail, these are onshore wells now, somewhere around 2%. Is that rare? 1 in 50? As the wells age, what happens to the failure rate? If you take an average here, it comes out of about 8–10%. And when the wells get really old, okay. Another way of looking at that is if we take the aggregate, the cumulative percent of wells that have failed over all their ages, it's between 4 and 5%. All right, so let's put together two things you learned tonight. In order for shale gas development to be economical, how many wells do they have to drill? A lot. Where? Everywhere there's gas. How frequently? 1 every 30 hectares. You've leased, or you've permitted for development to Southwestern 2.5 million acres. Is that right? 80 acres per well, that's 30,000 wells. If 5% of them show leakage over their lifetime, and that's an underestimate because the older they get, the more they leak, what's 5% of 30,000? It's 1,500 wells with problems. Is that rare? I don't think so. Does the industry know this data? Yes. All right, more recent data. This is 2011 data. Colleagues of ours at Duke University went into Pennsylvania and New York, and they tested a scientific hypothesis. They hypothesized that there must be a correlation between the concentration of methane in people's private drinking water wells and the distance of those private drinking water wells to the nearest shale gas well. That's a hypothesis. It might be true, it might not be true. How do you test a hypothesis? You do an experiment. What did they do? They went out and they tested the drinking water wells of 68 families. And they measured the concentration of methane in those drinking water wells. And then they used plotting, GPS, to figure out the distance between the drinking water well and the nearest shale gas well. And this is what they discovered. Horizontal axis is the distance between the tested water well and the nearest gas well. The vertical axis is the concentration of methane in milligrams of methane per liter. Look at it for a few seconds, and then you tell me what it says. This is how I teach, you know, it's the Socratic method. You know, I talk for a while, you talk for a while, you tell me what you see, and then we discuss it. Okay, who's the smartest kid in the class? Usually somebody in the front row. Right? Somebody in the front row is going to say, I know what that data says. It says if you're really far away, 5,000 meters, 5 kilometers, the probability that you're going to have a high concentration of methane in your well water is, well, it's below milligram level. It could be nanogram, picogram, microgram. I'm sorry, below, this is milligram. It could be below milligram is microgram. Who cares? If you got a microgram per liter of methane in your water well, you probably do. How many people here on private water wells? Okay. I guarantee you that you all have methane in your water. I guarantee it. But most likely it's at a level 1,000 times lower than this. It would not show up on this scale. But the data says the closer your water well gets to a gas well, what happens to the likelihood that you're going to have a high concentration of methane in your water well? It goes up. There's a correlation. It says if you're within about 1 kilometer, 1,000 meters, the probability that you're going to have a high concentration is fairly substantial. 70% of the wells within 1 kilometer had large concentrations, high concentrations of methane. High, by the way, in the US, if you're at 10 milligrams per liter, that's danger signal. Do something. If you get to 28 milligrams per liter, run. Do not light a match. Do not operate your cell phone. Get the hell out, because you're about to have an explosion. You're at the explosive limit. Okay? So these wells, for those people, these water wells, are dangerous to their homes. That's a correlation. That's not a causality proof. We can't say that the reason why all this methane was in those wells was because it came from the nearest gas well. That requires additional study. Geophysical study, geohydrological study, which is now ongoing. But it's very suspicious. Okay, so let's take that myth. The truth is that fluid migration from faulty wells is a well-known phenomenon. It's been happening since wells have been drilled, since the 1820s. It's a chronic problem. It won't go away. It will not go away. The industry has been trying for over 100 years to invent better cements, and the cements they have today are much better than the cements from 20 and 30 years ago. They've modified their drilling practices, their casing practices, the strength of their casings, the durability of their casings, the corrosion resistance of their casings, the flexibility of the cement, the sealing properties of the cement, the anti-shrinkage properties and anti-cracking properties of the cement, and it still happens. It will always happen. It is not a problem that will ever go away. Therefore, it's chronic, and we know it's going to happen at what rate? Rare? At least 1 in 20. Is that data borne out by the recent developments in Pennsylvania? Data that I didn't have time to put on a screen. In the first 9 months of 2011, you can check my data. You can go to the website of the Pennsylvania Department of Environmental Protection, where all this data is open to the public. I hope that your Natural Resources Department will open its data to the public. You can go look at all the violations of all the wells, what fines were paid, when the violation occurred, what the violation was for, exactly what regulation was broken. In the first 9 months of this year, there were approximately 1,200 new shale gas wells drilled in Pennsylvania. 65 of them were cited for loss of wellbore integrity. What percentage of 1,200 is 65? 5%. Modern technology, today, this year, best companies operating with best practices. Best practice does not mean perfect. Don't be deceived. Best practice does not mean no problem. Best practice just means the best you can do to minimize the problem. And the best you can do is 95% of the time, initially, you get it right. What's the health impact? There will be contamination of underground sources of drinking water. If there is large-scale shale gas development anywhere, and that anywhere is underneath or near people's private drinking water wells, some of those drinking water wells will go bad. It's a fact. Can't be avoided. So when you hear industry or government say, we will have really tough regulations such that we will avoid, prevent, prohibit any environmental problem, that is unadulterated BS. I don't know if you use that phrase up here. Okay. So, contamination of underground sources of drinking water with drilling fluid, frac fluid, and released hydrocarbons is a sure thing at a reasonably well accepted known rate from the industry. Can you now calculate the economic impact of that rate? What is the value of one private water well? Well, somebody would say it's priceless, but you would say, well, that property has now ceased to have its original value. You have incurred a recurring cost to supply that family with drinking water in some alternative way, and clearly there's a price associated with that. Can that cost be estimated and counted in your balance of good things and bad things from, cost-benefit ratio? Sure. Has it been done? Can I do another one? The use of clustered multi-well pads reduces surface impacts. This one is the one that really irritates me because it's the most logically flawed statement. So the industry says, if we were to go into your 2.5 million acres that are permitted right now, and we were to drill a well here and then go a kilometer away and drill another well here, and then go a kilometer away and drill another well here, you know, we're not going to do that. We're going to reduce that surface impact by just putting a pad here and then going a kilometer away and putting a pad here, and each pad's going to have 8, 10, 12, 16 wells. But wait a minute, that's apples and bananas. You would never, no company would ever drill one well here and then drill one well there and then drill one well there. It's uneconomic. They'd never do it. So the comparison is, if you're going to reduce impact, is either you drill or you don't. If you want to reduce surface impact, don't drill. But don't tell me you're reducing surface impact from a hypothetical that you would never do to the reality. That makes no logical sense. But they want you to believe it. So let's look at surface impact. Reality. How does surface impact really occur? What does it look like? Does anybody know what a 16-well pad looks like? Anybody been on one? Where? Okay. If you see something here that I'm showing that doesn't look right, let me know. Okay, showed you this picture before. Let's look at some other ones. This is the area. Here's the airport right over here, right off the map. This is the center of Dallas-Fort Worth. This is about 7 or 8 miles away. See all those white dots? Can you see them there? Is that clear? Every one of those white dots is a drill pad. I mentioned Dimock, Pennsylvania. Here's the town of Dimock. That's all there is. One intersection. No street light. Okay, here's a church. Here's the combined bar, restaurant, post office. I've been there many times. Okay. This is a 9 square mile area. Pennsylvania Department of Environmental Preservation declared that a restricted area because every one of these things is a pad. We can count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. 63 wells were drilled on those 39 pads in a period of about a year. 13 of those 63 wells went bad. Immediately. What percentage is that? It's about 20%, huh? And this was 2008, 2009. Okay, the poor people of Dimock had to deal with that, and so the Pennsylvania Department of Environmental Preservation shut them down. They took the company, Cabot Oil and Gas, and said, you can't drill here anymore. We're going to fine you over $1 million, biggest fine ever levied by the state of Pennsylvania. And we're not going to allow you to complete any of the other wells that you had intended. These were supposed to be 8 and 10 well pads. You can't do any more drilling until you fix the problem. 13 families that live along this road. You can see it right here, that road right there. 13 families lost their water wells. That's all of them. Every family living along that road lost its water well. And the state says, you restore the water to them as the law says, or you're not going to get permits. Just want to show you surface impact from afar. Let's get a little closer. This is a 16-well pad in British Columbia, BC, Horn River, northeastern British Columbia. 16 wells out of that pad. Notice that it is a fairly extensive industrial operation. This is not 1 hectare. Conventional wells typically need a pad of less than 1 hectare. What's happening in northeastern British Columbia is not unlike what I showed you happened in Dallas-Fort Worth under the airport. The pad I just showed you is this one. Here's another pad. Here's another pad. Pad, 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 pad. Notice the grid work, just like in the Dallas-Fort Worth airport. This is one company operating with one owner. 8 wells going in that direction, 8 wells going in that direction, and now you know why they go in opposite directions consistently. Let's go to the world's, what is claimed to be the world's largest shale gas pad. It's this one, also in British Columbia. Here it is. They had to build their own lake to store the 417 million gallons of water. Let's see, that's roughly 4 liters per gallon. So that's 1,600 million liters. Is that right? 78,000 tons of sand. Sand is used as the proppant. 32 million liters of fracking chemicals. 500 separate frac intervals. There's 16 wells here. The laterals were 3 kilometers long, and they needed 40,000 horsepower of fracking pumps to do the job. So that's heavy industrial activity. That's the surface impact. It's not minor, it's heavy industrial activity. And remember, on build-out, where would be the next pad? Right there, right there, right here, right here, right here. Okay. So you not only have extensive surface impact at one place, you have, if the company has enough capital and enough equipment, that's happening simultaneously in a number of places. Okay. I'll skip this one for now. Let's go right to New Brunswick. You've all seen this map. I just saw it the first time last week. I guess we're right about here, is that right? Okay. And I understand there's lots of development going on in here, and this is the SWIN permitted area. So I've gone ahead and gone to Google Maps, and I've taken an area just north of Fredericton, close to where Stephanie lives. So that's this map right here. And now I'm going to take and put together everything I've taught you tonight about shale gas development, and I'm going to try to give you a picture of what development would look like in that area if one operator, SWIN, got permission from one owner, the province, to ideally develop shale gas, if in fact there is gas in the shale there. They don't know that yet. But if they did, what would everything I told you look like? Each one of those yellow rectangles would be an area in which they would put a red dot. The red dot is the pad. And coming out of the pad, what would they do? Is that unlike the pattern I showed you at the Dallas-Fort Worth Airport or the pattern in northeastern British Columbia? No, it's exactly the same pattern. That's the way to get the gas out. The gas is everywhere there's shale, drill everywhere. How? Make sure you orient your wells such that they intersect as many joints as possible, because the joints contain most of the gas and are superhighways for the gas to come back to the well. If you're going to drill, in this case, north-northeast, then drill south-southwest. Cluster the pads such that you optimize your money. That's what it would look like. I'm not saying that's what it will look like, but under ideal conditions like the ones I showed you in northeast BC and in Texas, that's what it would look like under ideal conditions. Am I blowing smoke? Am I just inventing this, or is this actually happening in other places? This is a map of a county, Tioga County in Pennsylvania. This is the Pennsylvania-New York line. I live right here, about, I'd say, 30 miles from this line. Shell put together this map to show to the Environmental Protection Agency of how they were developing their holdings, their lease holdings in this county. So Shell went in competition with 74 other operators in Pennsylvania and cut deals with the landowners. Most of the land in Tioga County has been leased by Shell. In the United States, the mineral rights, I should have told you this, mineral rights vest with the landowner. Okay? So the company has to deal individually with every landowner. But they can get the landowners to agree, every one of these rectangular areas, every dot is a pad, every rectangular area is a spacing unit in which there are going to be multiple wells coming out of that pad. So that's the way it's developing in Pennsylvania. So you shouldn't be sitting here saying to yourself, it can't happen here. If the 3D seismics and the experimental wells that are currently being done determine that there is an exploitable amount of shale gas in New Brunswick, this is the way it will happen. That's my most important message to you tonight. And if you didn't know that that's the way it's going to happen, now you know. Forewarned is forearmed. All right, truth. The use of multi-well pads and cluster drilling does not reduce surface impact. Zero surface impact is what you have now. All right? They would never develop one well at a time. It's uneconomical. It doesn't make any sense based on everything I've told you and based on all the experiences I've shown you from other places. So it does facilitate and prolong intense industrialization and leaves a larger long-term footprint. How long does it take to drill and frack 16 wells? Years. During that time, there's heavy equipment operating, diesel equipment. So you're getting noise pollution, dust pollution, NOx pollution, light pollution, because this goes on 24/7, and weather notwithstanding, 365. So it's a continuous operation. What I haven't shown you, by the way, is all the ancillary equipment, because it's not just the wells and the drill pads. As those of you who live around here know, there's a compressor station around here someplace, right? There's also going to be a processing station if it turns out that your gas is wet. If your shale gas contains natural gas liquids, ethane, butane, propane, those have to be separated out at a processing plant. And we'll talk about flaring in a minute. All right, so the health impact is that you're going to have long-term noise, dust, light pollution, NOx emissions, higher spill probabilities of frac fluid because of the high intensity of wells per unit area, and the high frac fluid volumes necessary, and the high frac fluid waste return volumes that are necessary. There's going to be venting and fugitive emissions of produced gases. So let's talk about produced gases, the last myth I want to talk about. And by the way, if it's getting late at night and you have to go, go. Read those kids their nighttime stories. Last one. Natural gas is a clean fossil fuel. True or false? No, come on. As it's written, it's true. If I take an energy equivalent quantity of coal, oil, and natural gas, they contain the same amount of energy, and I burn them, which of those three fossil fuels produces the most carbon dioxide? Coal. Which produces the next highest amount of carbon dioxide? Oil. Which produces by far the least carbon dioxide? Natural gas. Is natural gas a clean fossil fuel? When you burn natural gas, it is cleaner than coal or oil. That's a true statement. Is that a true statement? Why? Because, wait a minute, hold everything. We better take everything into account. I mean, to get the gas out of the ground, you got to drill a hole. You got to create a pad. You got to drive trucks. You got to operate equipment. And then you got to frack it. And then when it comes back, what comes back with the frack fluid? A lot of gas. And what are you going to do with that gas? Some people say flare it. Well, not always. There are entire states in the United States that prohibit flaring. Well, then what happens to the gas that comes out during drilling and during fracking? Where does it go? If it doesn't go into a pipeline, which isn't going to be there every time, it gets vented. So, all right, some background. Why should we care? This is Climate Change 101. Graph, this is why they call me Ingraffea. Pretty good, huh? You know, if my ancestors, never mind. Last 5 years of data from the National Oceanic and Atmospheric Administration of the United States, which has the task given to it by the IPCC of monitoring the carbon dioxide concentration in the Earth's atmosphere. That's this, parts per million of carbon dioxide in the Earth's atmosphere. Notice that it's continuously increasing at a rate of about 2 parts per million per year. We're currently at about 390 parts per million. Relative to where we were 100 years ago or 1,000 years ago, that's pretty high. So what? All right. Global climate change, very much dependent upon greenhouse gases. Carbon dioxide is a greenhouse gas. Most reputable scientists allege, because they're scientists they can't prove, but they allege, that if this concentration gets to 450 parts per million, we reach a point called a tipping point where climate change will be so intense that we will be hard-pressed as a species to make it go backwards. And we might be hard-pressed to adapt to it. That's way out there, that 450. In fact, what it might do to us, no one really knows for sure, but we do know that if we're already experiencing climate change, at 390, 450 is going to be significantly worse. If carbon dioxide is increasing at 2 parts per million per year and 450 is really bad, how many years do we have? 30 years. Remember that number. That's carbon dioxide. Methane is also a greenhouse gas. What's methane? Natural gas, CH4. Why is that important? Well, here's a graph, again, starting with the year 1000 up to the present, of methane concentration in the Earth's atmosphere in parts per billion. So the concentration of methane in the atmosphere is on the order of 100 to 1,000 times less than the concentration of carbon dioxide. But as you can see, since the beginning of the Industrial Revolution, the concentration of methane has gone up, some would say exponentially. So what? So what is that methane is a much more potent greenhouse gas than carbon dioxide. Here's a molecule of methane, CH4. Here's a molecule of carbon dioxide, CO2. This molecule absorbs heat in the atmosphere many times greater than the ability of a carbon dioxide molecule to absorb heat. What do I mean by many times? Depends upon how long you want to look and how long the molecule is resident in the atmosphere. If you take a long look and say, well, let's look out over 100 years, it turns out that that methane molecule is about 33 times more potent than a carbon dioxide molecule. One methane molecule over a 100-year period will absorb as much heat as 33 carbon dioxide molecules. If you back off and say, I'm only worried about the next 20 years, because if we get to 30 years, we're toast. Pardon the pun. If I'm only worried about 20 years, that ratio goes from 33 to 105. One methane molecule absorbs as much heat as 105 carbon dioxide molecules, which means even a small amount of leakage of methane into the atmosphere has the same effect of a large amount of carbon dioxide by a factor of 100. Okay, how does methane get into the atmosphere due to the unconventional development of gas from shales? During initial drilling and frac fluid flowback, as I'll show you with another video, there's a large amount of methane emitted into the atmosphere. There's routine and continuous venting and leaks at the well pad. Count the number of joints in all of the equipment on a well pad. Okay. During liquid unloading, during gas processing, and during transmission, storage, and distribution through pipelines, there is leakage. There's purposeful venting whenever there's an overpressurization, whenever there's a compressor going on, there's purposeful leaking to control pressure. There's also fugitive emissions, leaks that you don't intend which are there. Aging gas pipelines, for example, compressor stations that aren't maintained properly, valves and fittings that aren't maintained properly. How much of the gas leaks? We'll get to that in a minute. Let me show you what it looks like on a well pad. So now we're back in Dimock, Pennsylvania, early this year. This well is being flowed back. That is, the frac fluid is coming back up. The gas in it is not being flared. Where's it going? Well, it didn't go into a pipeline. You can't go into a pipeline initially because there's so much water, contaminated water, coming back with the gas that you don't have a separator that's big enough to separate that all out. So you let the fluid flow into a big pond, and you let the gas escape through a vent pipe. I'm going to show you what it looks like, but I'm going to show you what it looks like in false color because you can't see the gas. Remember, methane is colorless, odorless, tasteless. This is a regular photograph. Here you can see water vapor. When the stuff comes up, it's at 150 degrees C, and so you get water vapor that's evaporating into the atmosphere. You can see that with the naked eye. But if we go to the next slide, anything that you see in the video I'm going to show you that's yellow is a hydrocarbon gas. Most likely, in this case, mostly methane, because it's dry gas in this region. This is a video that was taken with a forward-looking infrared camera that is tuned to show in false color something you can't see with the naked eye, a hydrocarbon gas. Remember, methane is lighter, less dense than air, so it's naturally going to want to rise. It's also hot, so when it comes up to the surface, up it goes. To give you a scale, these are treetops. There's a bird that just flew across, and eventually we're going to pan back so we can see that piece of heavy equipment that you saw on the previous slide, so you get a scale. And there's the piece of heavy equipment. So this is not just a little leak, it's a billowing of methane. And that goes on for hours or days during the flowback period. All right. Let's talk about a processing plant. Again, if you've got wet gas, you're going to need processing plants. You've got to separate out the natural gas liquids and the methane so that you can make money on everything. Ethane, butane, propane, everything goes to its right place. So my friend Bob Donan was driving through the Washington County, Pennsylvania countryside last September, and he saw this smoke in the distance. He zoomed in, and he saw that it was actually a flare stack at a processing station, burning off stuff that they couldn't process. And that doesn't look right. I mean, I wouldn't want that in my backyard. So he came back a few days later. This is September 18th, 2 o'clock in the afternoon. He came back 10 days later, roughly 7:30 at night. There's the flare stack, still going. It's still going now. And it will go as long as they're processing gas. Okay. So again, this is incomplete combustion. So there's molecules of whatever hydrocarbons are being combusted there going into the atmosphere. So what? I like asking that. Makes you think. So what? Where's he going with this? Last graph. This is a graph that compares the greenhouse gas footprint of both carbon dioxide from burning and methane from purposeful emissions and fugitive emissions for the three fossil fuels: diesel, coal, and coal can either be deep mined or surface mined, conventional gas development, and shale gas development. Okay. The direct burning produces the carbon dioxide, that's the black. There's indirect carbon dioxide from all the equipment that has to be operated to produce the gas. And then there's the methane that's also emitted. And what our data shows in a paper that we published in a peer-reviewed journal earlier this year is that our lowest estimate, because we don't have great data yet, so we made a high estimate and a low estimate. Our lowest estimate shows that, contrary to the myth that natural gas is a clean fossil fuel, taken over its life cycle, including not only its burning, but also its emission of methane into the atmosphere, makes it dirtier than coal and dirtier than oil. And if we take our high estimate, which of course nobody believes, we think the actual answer is somewhere in between. Take the high answer, then it's much dirtier. Even conventional gas, our low estimate, makes it about the same as coal and oil. So there's no free lunch here. You can't say, well, we'll get off of coal and oil and we'll just transition the whole world to burning natural gas. Does it help from the point of view of greenhouse gases and climate change? No, it doesn't. Since we published our paper back in April, there have been 7 other papers. 5 of them are shown here. 2 of them came out just in the last 2 weeks. I just want to summarize that some of those papers say we're wrong. The papers that say we're wrong either were funded by the United States government or by the industry. The papers that say we're right are either from independent environmental groups or from agencies of the United States government. So we have some agencies of the United States government, like the National Center for Atmospheric Research, which published this peer-reviewed paper, which says, you know, here's the amount, upper bound and lower bound of greenhouse gases. Here's our estimate. Here's that government agency's estimate. Here's a guy from our Department of Energy. He says, no, you're way wrong. It's only about half of what you say. But everybody who says we're wrong, that's red, has skewed their data in a couple of very important ways. First of all, they say we should only be looking at the 100-year time frame. You remember, at 100 years, methane is only 33 times more potent than carbon dioxide. We did both, the 20-year and 100-year. They said, no, we should only look at the 100-year because we don't want to look at the 20-year. And then they said the global warming potential, this ratio of heating values of methane to carbon dioxide, they say over 100 years it's 25. Well, the most recent science, published in 2009, says it's not 25, it's 33. This data comes out from a 1996 report done by the industry. This comes out from a 2009 report done by NASA. So we're using factors of 33 and 105. They're using factors of 25. And if you use our factors on their data, you get the same numbers we got. So they're skewing us to look at the 100-year time frame, and they're using old science, and they're only concentrating on electricity generation, and only about 20% of natural gas is used for electricity generation. The rest of it is used for heat generation. And so we took it into account, both electricity generation and heat generation, to cover the whole field. The point I'm making here is that this is science that didn't get started until April of this year. First paper came out in April. Before then, there was no science in the public domain. Since then, there's been a lot more investigation. The investigations are all pointing towards the fact that we were more or less right. The one I want to point to finally is the most recent data from September of this year by the United States Environmental Protection Agency. And their best number is 0.75, which is about in the middle of our higher and low estimates. So we agree with EPA, EPA agrees with us, and eventually it'll all work out. So, truth, over its life cycle, unconventional natural gas is likely no cleaner. We think it's actually dirtier than its fossil fuel companions, coal or petroleum, and even conventional gas, now that the data is finally coming in and the science is being done, is on par with coal and oil as far as its impact on climate change. So what? What's the impact on human health? There can be no larger impact on human health than that which impacts all humans, called climate change. And so development, I hope somebody checks my numbers here because I haven't finished the calculation. It is alleged in the material that I've been sent before coming up here, it is alleged that underneath New Brunswick is 63 trillion cubic feet of natural gas. No one knows because the testing is just now getting started, but it's alleged that there could be as much as 67 trillion cubic feet. If New Brunswick develops that gas and it all gets burned and or emitted, it would put so much carbon dioxide into the Earth's atmosphere that it blows the carbon budget for all of North America for 20 years. Check my numbers. I could be wrong. In fact, I probably am wrong to some degree, but it's a lot. Okay? So be careful what you're responsible for morally because, you know, everybody's downstream of what you do here with your gas. That's what I'm telling people in New York State, my home state, and that's why we still have a moratorium. You have a responsibility not only to yourselves and your fellow citizens in the province, you have a responsibility to humankind. Summary. I'm almost done. All right, I'm going to let you read those because I've said all these things numerous times tonight. This is just a recapitulation. And by the way, I will leave behind this presentation or give it to whatever organizations are capable of distributing it to whoever wants it. So you don't have to take notes at this point. Those are the big three. Probability of accidental releases because of the scale of the activity goes way up compared to conventional. The cumulative effects on human health and environment are not yet known because it's a young technology and those studies are just now getting underway. And finally, it's going to blow the budget on greenhouse gases. If you want more good, solid information, I have two recommendations for you of websites. One that I helped create, physicians, scientists, and engineers for healthy and sustainable energy. We vet government reports and peer-reviewed literature, and we either post it or review it and point you to it on this website. It's a very deep website. You can spend hours finding all this stuff on it, but it's high-quality stuff. We do not blog. We do not post anything that is not reviewed, peer-reviewed, that does not come out of a reputable government organization, and that is anonymous. We just don't do that. There's enough of that junk out on the web right now. We don't want to add to it. If you don't want to go to our website, there's one that's even older and still at this point better. It's the Oil and Gas Accountability Project of Earthworks. This website is even deeper. It has documents in it, which I strongly recommend that you download. One is called, What Happens When Gas Comes to Your Town? So it's a primer on everything you want to know about what to worry about, what to think about, what to do, what not to do when gas comes to your town. So I recommend that you look at those. And at this point, I want to say thank you very much for your attention. Thank you for your patience. I know I've blathered on here longer than you expected, but I'm willing to stay as long as you tonight. So feel free to start asking questions. So thank you.